What I'm going to show you in this video is how to determine the structure of covalently bonded molecules. So I'm going to be talking about molecules, and these molecules form because there is a sharing of electrons between nonmetals. So it's different than the ionic bonds, which were formed between a nonmetal and a metal. These are bonds between two or more nonmetals. So what I'm going to do is I'm going to give you some rules. Now what makes a covalent molecule a little bit more complicated is you can have single bonds between atoms, you can have double bonds between atoms, and you can have triple bonds between atoms. And what that means to you is that there's a lot more possibilities for molecules, their structures, than there were in ionic compounds. Ionic compounds were kind of boring. They were just positive and negative ions all stuck together like magnets in a crystal lattice. Here, covalently bonded molecules take on some really intricate shapes that we'll talk about. So what I'm going to do is I'm going to draw three dot diagrams, one for OCl minus, one for a molecule CH3OH, and another molecule SO2, make that SO3, 2 minus. Now, two of those are polyatomic ions. They're molecules that have ionic charges to them because they've gained electrons from somewhere else. And one of them is a molecule. Now, the first thing that you want to do is you want to count valence electrons. So I'm going to count all the valence electrons in each of those molecules. So if I'm sitting there doing the OCl minus, oxygen has 6 valence electrons. Chlorine has 7. And since it has that negative charge associated with it right there, I'm also going to add one more electron to its valence shell. So when I do that, I end up with 14 valence electrons. Now these are going to be the electrons that I'm going to use to build that molecule. I'm going to do the same thing for this CH3OH. Carbon has 4 valence electrons. I have 4 total hydrogens. So 4 hydrogens at 1 apiece will be another 4 valence electrons. And then the oxygen, again, is 6. So when I add that up, again I have 14 valence electrons as my total. In the SO3 minus, sulfur has 6 valence electrons. I have 3 oxygens at 6 apiece, makes 18. And just like in the OCl minus where I added an electron because of the negative charge, here I'm going to add 2 electrons because there are, well, because that's what the formula says, so I'm going to add a 2 to that total, and I end up with 26. Alright? So these are the electrons that I'm going to use to build these molecules. Alright? So now what I want to do is I'm going to draw what's called a skeleton structure. So I want to draw a skeleton structure. Okay? And the way I'm going to do a skeleton structure is I'm going to connect all of the atoms with a single bond. Now, usually the central atom is written first in the formula. Well, the first one that I'm going to draw is the OCl, and there's only one way I can connect those together with an OCl because it's just a diatomic molecule and there's nothing else I can do. In the CH3OH, carbon is written first. So that becomes the central atom, and I want to sort of always be branching off of that into 4 possible bonds. That's the basis of all covalent molecules, is to have 4 bonds. You'll understand why that is, because each bond is represented with 2 electrons. 2 times 4 is 8. I'm back to my octet, and that's good. So I'm going to come up with this structure as a skeleton for CH3OH. Carbon in the middle because it's written first. Hydrogens always terminate. They're always at the end. There's nothing, hydrogen can only have 1 bond to it. Oxygens usually only have 1 bond to them, sometimes have 2. Halogens only have 1 bond to them. Then my final one, put sulfur in the middle because it's written first, and then the oxygens coming off of that. So that was my second step right there, is to draw the skeleton structure. Now my third step is going to be to subtract the number of bonding electrons from my total valence electrons. In my first example, I had 14 valence electrons, and now I look up here and I have 1 bond. That 1 bond represents 2 electrons, so I want to subtract those 2 electrons from my valence. That leaves me 12 valence electrons left over. In the CH3 OH, I had 14 valence electrons that I added up. But here I have 1, 2, 3, 4, 5. 5 times 2, 5 times 2 makes 10, all right? So I'm going to subtract 10 from my 14, leaving me 4 valence electrons. Okay? Let me get rid of that. Kind of annoying. Now, my last one, I had 26 valence electrons. And here I have 1, 2, 3. 3 times 2 is 6. So I subtract 6 from it, so I have 20 left over. Alright? Now, those are the electrons that I'm then now going to place around the all the atoms to ensure that each atom gets 8 electrons around it. So it's going to look like this. Okay, and so I got to draw those again. But this is what I had. I had OCl. I had a C to an H, 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 OH, and then I had the S to the O, O, and O. And from those calculations, I had 12 electrons to work with on this one. I had 4 electrons to work with this one, and I had 20 electrons left over to work with that one. So here's how I'm going to do it. I'm going to take those 12 and I'm going to put them around every atom to try to get 8, just like drawing any other dot diagram. So with my 12, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There, I used them all up. Every atom in this molecule has 8 electrons around it, because you got to remember that this single bond right there represents 2, so it's sharing between them. Now that was an ion, so I want to finish it off by just putting it in brackets and designating the fact that it's negatively charged and it got an electron from somewhere. I'm going to do the same thing with this one with 4. Well, the carbon has 8 because it has 1, 2, 3, 4 bonds, 2 apiece. That makes 8. The oxygen only has 4. Well, if I take those 2 or 4 remaining electrons, put around the oxygen, now everybody has 8 with the exception of the hydrogen. Hydrogens only need 2 bonds. So I took care of that one. Now the last one, I have 20. So here goes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There it is. That molecule is the way it's going to look because it has 8 around everybody. I have 8 there, I have 8 there, I have 8 there, and I have 8 there. I used them all up. Okay?